Okay, so thank you very much for the invitation. So let me write down the title, Decompositions and HMS. And so homological mirror symmetry for surfaces. And I should say that this is based on 3 papers that I wrote together with James Pascaleff, and there is still a work in progress. So joined with Pascaleff. The first paper is now a few years old, and the last paper just appeared last summer. So what I'd like to do is I'd like to start with a survey of homological mirror symmetry for Riemann surfaces. From the perspective of sheaf-theoretic methods. Sheaf-theoretic methods. What does it mean? Well, I'll enlarge actually my slide in a second. What does it mean? It means that in the Fukaya category, methods have been developed to perform local to global computations. At the beginning of the subject, this was considered one of the biggest obstacles in calculating the Fukaya category, and something somehow the one could never achieve. Famously, one would say there are instanton corrections which are global in nature, so you cannot confine them to any local region of your symplectic manifolds. But in the last, I would say, 15 years, have emerged techniques that in some settings allow us to do that. And typically, they were in settings in which the symplectic manifold would be non-compact. And one of the things that I'd like to tell you about by the second half of this talk is that actually some of these methodologies carry over to the compact case. So now we have a sort of a framework to understand locally the Fukaya category of compact symplectic varieties. So the beginning of my talk has been the same, I think, for 10 years. So I apologize if you've seen this already. And this homological mirror symmetry for P1. For P1, and I would say that this is based on just wonderful ideas of Bondal that then were worked out and expanded on by Fang, Liu, Truman, Zaslow, and many other people then worked on this. So what I'm going to tell you is a possible formulation of homological mirror symmetry for P1. And the way this will work is that I'll write down a sequence of categories and equivalencies between them. And when we compose these equivalencies, we will see that we can interpret the resulting equivalence as a homological mirror symmetry statement. So the first category lives in the world of algebraic geometry, and is the derived category of P1. The second category lives in the world of representation theory. Let me just indicate it with RT, and is the category of representations of the Kronecker quiver. I will say once and for all that all the categories appearing in this talk will be triangulated and DG enhanced. So the equivalence between these two categories is a famous theorem of Beilinson from the end of the 70s, which was the starting point of the modern study of the derived category. So people really understood that you can compute the derived category. Before, it used to be just a sort of a convenient object to prove other things, but it became an object of study in its own right with this result. So the third category lives in the world of topology. And it's the category of constructible sheaves on S1 stratified by a point. So let me denote this like this. So what does it mean, constructible sheaves? Well, it means that these are sheaves of complex vector spaces that are constant on this point, this red point, and on the complement. And of course, we're always taking, as I said, the triangulated category of this object. Well, this equivalence is also a simple instance of a very beautiful story, which is the exit path formalism of, say, this starts with Macpherson. I hope I'm spelling the name of Macpherson right. And it has been studied. A reference, modern reference is an appendix to I think higher topos theory of Lurie, or maybe higher algebra. So, and finally, the last category, which I will have to indicate below. So the last category, here there is an equivalence, is a category which is symplectic geometric in nature. And this is the Fukaya category of the star S1. Let me say relative to lambda. I'll explain what this means. And so this is a beautiful theorem of Nadler and Zaslow. So the Fukaya category is an invariant of symplectic manifold. A cotangent bundle always has a canonical symplectic form. And here we are looking at the Fukaya category of the cotangent bundle of S1 relative to some decoration that I will explain, whose meaning I will explain in a second. If you put together all these equivalences, you see that you have an equivalence between the derived category of a certain algebraic variety and the Fukaya category. This is exactly the format of Kontsevich homological mirror symmetry, at least one direction of Kontsevich homological mirror symmetry. So let me explain the Nadler-Zaslow theorem. So theorem Nadler-Zaslow says the following. So if M is an analytic manifold, and lambda contained in T star M is a conical Lagrangian, so what does it mean, conical Lagrangian? Well, we see an example in a second, but Lagrangian is a Lagrangian in T star S1, so it's a subspace such that the symplectic form pulls back to zero, which in this case for dimensional, in T star M, such that the symplectic form pulls back to zero. And conical means that is invariant under dilation, the action of the positive real numbers on the fibers by dilation. So we'll see an example in a second. So by giving this data, what we have is that we have an equivalence between the Fukaya category of the cotangent bundle relative to lambda, and I'll explain in a second what this means in the example that interests us, and the category of constructible sheaves on M with so-called singular support in lambda. So, let me not explain what a singular support is. It's a more general notion of a stratification. But let me explain what this theorem says in the example that interests us. So in the case we discussed, in our case, we have the cotangent bundle of T star S1, and then here we fix this lambda. So this is lambda. Lambda in this case is just the conormal to the circle, which gives the circle, and the stratum, and the conormal to a point is the cotangent fiber. So it's the union of the of S1 and the cotangent fiber. And let me make a comment here. So in this case, so this is a general theorem, constructible sheaves on S1 with singular support in lambda is the same as constructible sheaves on, as we said, S1 stratified by the point. Okay, it's just a different way to say the same thing. So that's what we have, and lambda is clearly conical because it's invariant under dilations, because it's a whole sort of cotangent fiber under the base. And this Fukaya category that we're looking at, well, is the Fukaya category of those Lagrangians which are free to sort of wander around here. So Lagrangians in this case are just curves in this cylinder, but towards infinity are required to go asymptotically close to lambda. So the purpose of sheaf-theoretic methods in the study of the Fukaya category, and let me write a few names here. So well, Nadler-Zaslow, which we already mentioned, further contributions from Nadler, from then Kuntsevich gave a very big impulse to this line of research. Dikharov and Kapranov, and let me just, there are tons of people that contributed. GPS stands for Ganatra Pardon-Chende, which are really developing the foundations of this theory. Sheaf-theoretic methods in the Fukaya category aim at generalizing this simple picture to symplectic manifolds of the following form, the following type. So let's consider, for instance, something like this. So this is a genus 1 curve with two punctures that I'm sort of indicating with these boundary points, boundary components. And here I'm drawing what is called a skeleton. So so this is this sigma. So sigma is an exact symplectic manifold. Exact means that that we can write that the symplectic form omega is d theta, where theta is a one form. Cotangent bundles are the prototype of exact symplectic manifolds. So this is exact, like just like the cotangent bundle, but it's not. But it is not globally a cotangent bundle. So basically, the point of these techniques is that we know how to compute the Fukaya category of cotangent bundles. Now we have objects, geometric objects that are only locally like a cotangent bundle, and we want to get some global description of the Fukaya category by sort of patching together the Nadler-Zaslow theorem. This would be a sort of an angle on these techniques. So here's the idea. If X is such a symplectic manifold, I'm sort of ignoring some subtleties, but dealing with surfaces, they don't really play a role. So such a symplectic manifold, we can equip it with a skeleton. So I haven't told you what a skeleton is. I'll do it in a second. I've just drawn a picture there. And the Fukaya category of X will localize over the skeleton. So what is the skeleton? So is a, sorry, I see there are some questions. Okay, fantastic. So we can just ignore the datum of the one form. It doesn't really play a role in this game. Well, if you want, you can take, for instance, an embedding of the torus in projective space, and restrict the Fubini study, and then restrict the Fubini study to this open patch of the torus, so the elliptic curve, and this, for instance, would work. So we were saying the skeleton is a Lagrangian deformation retract. So for our purposes, this is enough. So it's something like a gamma that sits inside sigma as a Lagrangian. In this case, for dimensional reasons, any curve is Lagrangian. But furthermore, gamma is a deformation retract of sigma. So anyways, that's what skeleton are. What does it mean that the Fukaya category will localize over the skeleton? It means the following. It means that there is a sheaf, or rather co-sheaf of categories F on gamma. So let's call the skeleton gamma, having the following properties. So such that one, the global sections of F of gamma compute the Fukaya category of X. So here I should decorate it with wrapped. And two, locally, F of U is given by some category of constructible sheaves. Let me just write it. I'm sorry, I'll change the orientation of the tablet in a second. I don't know why I haven't done it yet. And this is the same as, would be the same as rep Q, where Q is a quiver. So what is the idea here? So the point is that the global sections of this sheaf compute something that we're really interested in, the Fukaya category of X. So equivalent with relations. Yeah, thank you very much. Although in the case of Riemann surfaces that we are treating here, there will be equivers without relations. So there's something that we really want to understand, which is the Fukaya category of this global object. And the point is that we can patch it together from local categories, which are very computable. So that's the That's the idea. And let me make a remark here. So remark. So if X is equal to T star M, so is a cotangent bundle, and gamma contained in T star M is a conical Lagrangian, then what we're saying, then we are saying that there is a natural sheaf of categories over gamma such that the following is true. So such that one, so let's call the sheaf of categories microlocal sheaves. So such that the global sections of the sheaf of categories over gamma computes the category constructible sheaves on M with singular supporting gamma. Right. Yeah, sorry. That's what we're saying. So let me erase this. And this is something classically known. So this is given by the theory of Kashiwara, Shapira, micro-localization. So, so this is a generalization of this technique. The theory of constructible sheaves is very important. It says not just, it's sort of obvious that it's sort of obvious that the category of constructible sheaves is local over the base M. That's what we would expect. But in this context, we have a further locality over something that lives over the cotangent bundle. This is exactly what we refer to as microlocalization. So when X is a punctured Riemann surface, understanding this sheaf F, understanding F, so the sheaf on the skeleton, reduces to the following. Sorry, I just let me also put on silent my phone. Reduces to the following. And again, it is slightly imprecise here. So this is equivalent to representations of the squiver. And then we have three restrictions here. Let me first write this down and then explain. So what I'm saying is, in the case of a Riemann surface, a skeleton is of the kind that we saw before. So let me show it to you. It's something like this. And the claim is that we can always deform it so that vertices are trivalent. We can always assume that we're dealing with a generic, so trivalent skeleton. Then the local categories are the categories that this sheaf F, the computed Fukaya category, attaches to trivalent vertices. And the claim is that to a trivalent vertex, we attach the category of representations of that quiver, which correspond to a certain category of constructible sheaves over the real line. So then to pin down the behavior of the sheaf F over the skeleton, you only need to understand its local sections. And so then, so let me maybe actually fill in a bit more this picture. So yeah, so you only need to understand its sections on a trivalent vertex, and then you need to understand the restrictions. So now what you attach to an edge is just the category of vector spaces. And so all you need to understand is this. What are the three restrictions from the representation, from the category representations of that quiver to category vector spaces? And you have three of those restrictions. One is the first sort of an object in that category is given by a vector space with an inner map, two complexes of vectors, or two complexes of vector spaces with a map between them. You can restrict to the first vector space, restrict to the second, or take the cone. And these are exactly the restrictions. So as you can see, this sheaf F, the computed Fukaya category, has a very simple local behavior. And this is enough to actually compute the Fukaya category of Riemann surfaces. And I should say, when we actually compute the so-called wrapped Fukaya category, we are dealing with co-sheaves rather than sheaves. And what we need to do is that we need to take left adjoints of those restrictions. And this will give us co-restrictions. And this is the co-sheaf we are looking for. So this point of view gives very easy proofs of homological mirror symmetry for some Daniel punctured surfaces, punctured curves. Sorry, let me write it like this for some nodal curves. So where the nodal curve is on the B side. So let me explain. So this by now is something that was understood a long time ago. So let's consider yes, absolutely. Yeah, exactly. That's how you deform a four-valent vertex to a trivalent vertex. Yeah. So let's consider on the B side a nodal elliptic curve. So something that looks like that. And then its mirror, and this can be justified under from many point of views, it has to be a torus with one puncture. And I'm also going to draw inside its skeleton. For instance, this can be justified by a Dessozy picture of mirror symmetry. So now we're going to express perf x as a certain limit of categories. And so let me do it. So we'll say that perf x correspond to the following equalizer in categories. So let me explain. What are we saying here. So this P1 is the normalization of X. And all we are saying is that giving a perfect context, but we can think also of a vector bundle over X, is the same as giving a vector bundle on the normalization together with gluing data. Gluing data means I'm on the normalization. I need to fix an isomorphism between the fiber at 0 and the fiber at infinity of this object on the normalization, so that it glues to give me an object on the nodal curve X. This can be sort of formalized in a convenient way by saying that perf x is this equalizer, homotopy equalizer, in the infinity category of DG categories, or in the model category of DG categories. And so now, on the other side, we can sort of exploit the locality of the Fukaya category to our advantage. So what we have is that the Fukaya category of X dual, so of these punctured torus, is given by so let me first write it and then explain. So we know that the Fukaya category of this punctured torus localizes over the skeleton. And so what we're supposed to do, you're supposed to take an open cover of the skeleton. Let's take this open cover. So this is one piece, and then this is another piece. Okay. And now the sections of F on the skeleton is basically the calculation we started with. Is the same of constant. You know, this looks not by chance like the conical Lagrangian that we saw in the homological mirror symmetry for P1 example. So basically from previous calculations, we know that these two categories are equivalent. And we also know that these two categories are equivalent. So what this sheaf of categories attaches just to an edge is the same as the category, triangulated category vector spaces, which is the same as perfect complexes over the point. Further, it's easy to see that this is a commutative diagram, and so this implies that we have the desired equivalence between these two categories. Okay, so that's how we use the locality on the Fukaya category. We use it by matching some sort of limit that we have on the B side to reduce to statements that are easier to prove. So now this story, so this is really sort of an historical overview, because by now I'm talking about results that are quite old. So this has had many generalizations. I'm going to mention this in a second. Yeah, I'm going to mention this in a second. So there are many generalizations. So the first one is that via this exact same reasoning, we can prove that punctured curves of genus 1 are mirror to Stucky nodal curves of arithmetic genus 1. then higher genus was worked out by Lekili and Polishchuk, and then in higher dimensions, there are various works. For instance, Gamage, Schende. Yeah, so let me address the question. So the question was whether this work for nodal curves in every genus, and the answer is no. The generalization is different. The right generalization is different. It will work in some cases. We'll see the sort of the general statement where this fits. So the whole point of this talk is that so more recent result is that it turns out that that Fuk in the exact setting has also a different kind of local to global behavior. And the sort of discovery that we made with James now a couple of years ago is that this persists in the compact setting. So that's what I want to tell you. So the first thing we noticed was the following. And I'm going to write this statement that will look not very enlightening and then comment on this. This is a sort of a precise symplectic meaning. So let's take a skeleton gamma. I just formulate it in terms of skeleton. And suppose that we have two closed subskeleton. So two closed subsets. And the important thing here is closed, such that they cover gamma and their intersection is controlled and is a disjoint union of S1s, but really the right condition is that what really matters is that sorry, let me draw this better, is that locally they look like this. So not just they meet in an S1, but they also come from the two different sides of that cylinder around that S1. So if this is true, then we have the following fiber product. Then f of gamma, which remember is computing the Fukaya category of X. F of gamma is a fiber product of categories. So the first thing, of course, is that one needs to define these restrictions. Remember, F is either a sheaf or a co-sheaf of categories, so it's not part of its sort of features as a sheaf that I have restriction functors to closed subspace. One needs to construct these restrictions, and then one proves that one has this fiber product. And the things to say is that this is really about having exact symplectic manifolds and doing Viterbo restrictions to what is called, so having a Liouville manifolds, exact symplectic manifold with a Liouville structure, and doing Viterbo restriction to Liouville subdomains. I'm just expressing this in terms of in the language of these ribbon graphs, because I think it might be closer to the audience, but this is the underlying geometry. And so as an example, it's very easy. Let us revisit homological mirror symmetry for P1 from the vantage point of this new local to global property of the Fukaya category. And so what we have is on the B side, here's the B side and here is the A side. And on the B side, we will have let me just write perf instead of dbco, but of course there's no difference since all these varieties are smooth. Perf A1, and here the fiber product is perf P1. Let me first try these big diagrams and then comment. And on the other side, we have that f of this graph can be computed as the fiber product of so this upper part, this lower part, and their intersection, which is S1. So this is a fiber product of categories. And now let me just say that basically the fact that these two categories are equivalent is basically definitional, and also the fact that this category is equivalent to this category. And so now again, we are able to deduce that there is an equivalence here, which is the equivalence that we desired, from pieces where the equivalence is obvious. This is a completely different proof. Is all, this is a very simple example, just to fix ideas. But notice that this is a very different proof compared to the one that we gave at the beginning, because, for instance, it doesn't use the fact that P1 has a strong exceptional collection. It uses something completely different. It uses just the fact that perf satisfies Zariski descent. So if I have an open cover, I can compute perf from the pieces. So the corollary of that statement of this new locality statement that we prove, the corollary is the following. So if sigma is a punctured Riemann surface, with a Pence decomposition P, then the Fukaya category of sigma is a limit of the Fukaya category of the Pence making up the composition of sigma. So perhaps we don't know what a Pence decomposition is, but this is what I mean. So it's something like So this is a Pence decomposition. What I'm saying is that now there is no skeleton in the picture. What I'm saying is that if I'm interested in the Fukaya category of this object, is enough that I understand the Fukaya category of the Pence, which I do. And so then, and again, also this is by now a result that we proved several years ago with James. So we can prove classical Hori-Vafa homological mirror symmetry exploiting this local to global principle. This is a question in which we have contributions from very many people. So Oru, Efimov, Katsarkov-Orlov, Oru Abuzaid, Efimov, Katsarkov-Orlov, Gross, Katsarkov-Rudat, Balkland. But here is basically the way we approach this question. So we have a B side and an A side. Sorry, I had to. This was one of the punchlines of the talk, which will return at the end, is that this kind of local to global behavior persists in the compact setting. That's the main thing. This makes sense in the compact setting for genus at least 2. I can find the pencil compositions, and the Fukaya category of this compact surface can be built up from the Fukaya category of the pencil composition. So I don't need to be in the exact setting of punctured Riemann surfaces. So on the B side, so now let me return to this Hori-Vafa homological mirror symmetry. I start with a polytope P equipped with a unimodular triangulation T. So for instance, something that looks like such. And then I can triangulate it. So for instance, consider something like this. Then we suspend this at height 1. So we take a cone over this. And this is the fan of a toric Calabi-Yau threefold X sigma that has a superpotential W to C. Okay, so what I'm saying is that I have this lattice polytope, I triangulate it, I place it at height 1, and I take the cone over this. This gives me a fan, and this is a fan of a Calabi-Yau toric threefold. And the height function in the fan gives me a superpotential. And so the category I'm considering on the B side is MF W. And the mirror of this, well, the mirror of this is computed as follows. I mean, I'm giving you sort of the purely combinatorial recipe without justifying it. But you take this same data, so a polytope with triangulation, you take this dual graph, and this dual graph is the tropicalization of a punctured Riemann surface. You see how this goes. And on the A side, we consider the Fukaya category of this. And the claim is that there is an equivalence here. This is what we prove. And how do we prove it? Well, we prove it because on both sides, so on this side, we have Pence decompositions. And on the other side, we have the natural toric affine open cover. So this geometry is covered by pieces, by pieces that just look like C3 or A3 with a superpotential XYZ. Okay, so these are the local sort of building blocks. And one proves this statement for the pair of pens. So the pair of pens is mirror to matrix factorizations of XYZ. This is the local case. And then one globalizes. On the B side, this is just Zariski descent for MF. On the A side, this is this descent for pens that I mentioned. So I'm sorry, I'm very late. So we have only 2 minutes, so let me pass so quickly to the compact case. So, as I said, the main point to take out of this talk is that this locality based on Pence decomposition persists in the compact setting. So what does it mean? So let sigma be a compact Riemann surface. Of genus G greater or equal to 2 and P appends decomposition, then let me just give you the result, and then explain maybe a bit of the proof. The idea of the proof is extremely simple. Is exactly so. The result is that the result is exactly the same that we had in the punctured case. So I have G with a Pence decomposition, and the Fukaya category of this compact surface is the limit of the Fukaya category of Pence. So let me briefly sketch. This has a number of applications and consequences, and unfortunately, some of them I won't be able to touch on. Also related to our most recent work. But let me try to say something here. So, what is the idea of the proof? Then, actually, the proof has sort of many complications, but the idea of the proof is very easy. So let's consider this sigma genus 2 with its Pence decomposition. And then let's consider sort of a combinatorial tropicalization. So a graph, say like this. If you want, this is the dual intersection complex of the Pence. So let me maybe slightly correct this picture. So what we can do is that we can take an infinite cover of this G, what we call the maximal abelian cover, which is something that looks like this. So pi, and then O pi is the group of deck transformation. And then we can take the fiber product here, which is an infinite genus Riemann surface. So sort of given by a fattening of this, no, this planar, this sort of tessellation. Well, so just the graph tessellation of the plane gives the tropicalization of this infinite genus Riemann surface. And the idea, although as I say, this requires a lot of caution actually to make this work. The idea is that sigma tilde, though it may be a slightly unusual character since it's not finite type, it's infinite genus, is still a non-compact, so it's still an exact Riemann surface. In fact, is Stein. And so its Fukaya category can be understood in terms of the sheaf-theoretic techniques we discussed at the beginning, and in particular, satisfies this descent by pens statement. And so then one proves, so this is the first ingredient. So as I said, the idea is fairly simple, fairly natural. The first ingredient is, we pass to the sigma tilde, is non-compact, but is infinite genus. And then one proves that well, this Fukaya category, and again, I'm not giving details of how exactly which Fukaya category one should look at, as clearly an action by deck transformations, and the quotient, so categorically we would say the fixed points of this action in this category, compute the Fukaya category of sigma. This is nothing new in the symplectic literature. It's often done that we sort of reduce a knowledge from some, or there's a transfer of knowledge between the Fukaya category of a cover and the target of this cover. The difference here is that we have this not a finite cover, but is infinite. So it is infinite genus Riemann surface. But so this is the main ingredient, and then from descent by Pence decomposition on this guy, we manage to deduce. We can easily deduce this. Sorry. As I said, this is just a very rough sketch. Let me just say rapidly some of the corollaries. I wanted to mention some other things. Maybe if there will be a question, I can tell you something more. What are some corollaries? So the first one is the answer of a question by Haydn, Katsarkov, and Kutsevich. So all branes in Fuchs sigma are geometric. So they can be represented by an immersed curve in sigma. This is something that in HKK, so in HKK was proved this when sigma is punctured. And we are able to deduce this also in the compact case. So then let me just say all previous homological mirror symmetry theorems for compact curves so the famous result of Seidel and Efimov, sort of we recover this result, in a way demystifying these results, if I can use this expression, in the sense that Seidel and Efimov, they were very clever argument based on the finite generators. Here we just recognize that the A side and the B side have the same descent and the building blocks are the same. So pens on the A side and on the B side, sort of singularity categories of an especially simple type. Then the other side of beautiful work of Canizzo on HNS for genus 2 curves. So again, part of the advantage of this result is that you can immediately compute that something is the mirror of a compact Riemann surface just by descent. So you don't need specific sort of examples. So I could tell you more, but maybe I should stop here. Let me write just So sort of this is what I wanted to tell you, but I don't have time. So a vast generalization of Ori-Vafa homological neurosymmetry. And related to this, a sort of a perspective, an angle on Lekili-Ueda, on some conjecture, beautiful conjecture of Lekili-Ueda. Okay, so thank you very much for your attention. I think I should stop here and